Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webcast, Bridging the Great Divide, the Relationship of RDBMS and NoSQL, brought to you by Information Week, DataStax, and broadcast by United Business Media Limited. I'm Eric Bruno, and I'll be your moderator today. We have just a few announcements before we begin. You can participate in the Q&A session by asking questions at any time during this webcast. Just type your question into the Ask a Question text area below the video window, and then click the Submit button. At this time, we recommend you disable your pop-up blockers. The slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on the Download Slide button located below the presentation window. If you are experiencing any technical problems, please visit our Tech Webcast Help Guide by clicking on the Help link below the media player. In addition, you can contact our Technical Support Helpline, which is also located in the Webcast Help Guide. Now on to the presentation, Bridging the Great Divide, the Relationship of RDBMS and NoSQL. Discussing today's topic is Billy Bosworth, CEO, DataStax. Billy is responsible for the day-to-day operations of DataStax. He has 20 years of experience in the database industry in roles ranging from DBA to senior executive. Prior to DataStax, Billy spent 6 years at Quest Software, a provider of systems management software, where his most recent role was VP and GM of the database business unit. Under his leadership, the industry-leading Quest database business grew from supporting traditional relational databases to a portfolio that now includes tools for cloud, NoSQL, Columnar, and Hadoop databases, as well as business intelligence offerings. Prior to Quest, Billy led product teams for Embarcadero Technologies' database productivity solutions. Billy holds a Bachelor of Science in Computer Science from the University of Louisville. And now on to the presentation. Billy?
Thank you, Eric. And that intro makes me sound a little old, but the truth of the matter is I have been around databases for a very long time, whether I've been developing against them or administering them or writing tools for them. It's been in my blood for the last 20 years. So I'm very excited this morning to get the chance to talk to you. I'm calling you from downtown San Francisco, and it's my pleasure to spend a little bit of time with you today and see if we can bring some clarity to the challenges of understanding what is the relationship between the two of relational and NoSQL technologies. How I want to break this down is to walk you through a little bit of a timeline, because it gets very difficult to understand some of the things that are happening today and some of the things that might happen tomorrow unless you do have a bit of a foundation on how we got here in the first place. So we'll look at this in time slices. We'll take a look back, and then we'll take a look around, and then we'll take a look forward and see how all these things are playing out. The first thing that is important to understand is the problem of big data actually is not very new. 20, 25 years ago, we ran into this problem where we had certain systems designed for OLTP, and we'll talk a little bit about what that means and what that looks like, but it was transactional systems. It was real-time systems. And then we wanted to do deep analysis of that data. And to do that in the same database didn't make sense. You had a conflict of resources on the machine that would slow down the operations of the real-time system. And so the way we handled that was we moved the data around with a process called ETL, extract, transform, and load. And we pushed that data from these real-time systems into these bigger systems called OLAP systems. And in an OLAP system, which stood for Online Analytical Processing, that's where we would do our deep analysis. But the challenge of the different kinds of data and the different demands upon the data has been with us for quite some time. So in a sense, big data isn't necessarily a new challenge. That said, there are definitely some things that have occurred that make the modern big data problem quite different from the big data problems of the past. So to begin our journey, I want to start with this big guy here in the OLAP side, the data warehouse, and I want us to understand a little bit about how and why it evolved over time. Characteristically, the big names that you would see in this space were names like Teradata and Netezza and some of the stuff that Tivoli was doing. And we used to call this DSS, and it stood for Decision Support System. And anybody in the relational world 15, 20 years ago would absolutely know what you were talking about if you said, put this over in my DSS system or my data warehouse. It was optimized for a lot of batch reads and bulk writes. And what that means is when you would ask a question of the data in a data warehouse, you could do it in kind of a batch mode where you weren't as concerned about how fast that query was going to come back because the questions you were asking were very deep and very complicated. So what you would do is you would go ahead and submit the query and probably not expect things like a sub-second response time. It might actually take hours. In some cases, I was part of systems that took overnight before you would get your answer back. And the data would be pushed into these systems kind of all at once with bulk write activity. So you would do a transformation or a load of the data from a relational system or a flat file or the mainframe even into one of these data warehouse systems. Everything about it was designed for these complicated queries. So I wasn't asking a simple question. I was asking a question that would relate to a very complex relationship or an analysis over time or an aggregation of data rolled up into summary tables that would then help me answer or ask another question. So everything about the systems were optimized for that type of analysis. That's just the nature of how these systems work. And that's relevant. It's very relevant to the bridge and what happened today with the first movements in the big data world. One of the challenges with the relational model for big data on the data warehouse side was the way that you scaled. When the data got bigger and the demands got bigger, the way that you scaled that was what we called scale up, which just meant you bought a bigger machine. You bought a machine with more processors and more memory, and you would continue to push more and more and more onto a bigger and more powerful box, which was fine for quite some time, actually, because the way that the hardware would advance so quickly, it allowed you to keep up with a lot of the data growth. However, it was never accused of being inexpensive. This always was a process where you start to realize you're going to shell out some significant dollars to scale these solutions into a very big answer in the data warehouse side of the world for your OLAP systems. And that was the prevailing technology for a long time, a couple of decades. This is how we handled the big data problem in the past. But then a new kind of OLAP problem emerged. And there was this little company out there called Google who had a very big problem. They wanted to look at basically the whole internet, and they wanted to be able to study and analyze all of the activity that was going on around the internet. And this consisted of these things called logs from the web servers and the app servers. And the challenge with that kind of data was that it really didn't neatly fit into the way you designed a relational database, even data warehouse. When you thought about something like a log or even now a blog as time went by and the emails or the comments that would happen on social sites, that type of data is different than the simple row column data that you would put into a relational database. And this caused some very real challenges. It caused challenges on how you designed the system. It caused challenges on how the system performed. We would try and force fit it, and I did this for a big part of my career, was trying to fit data types that were not really around or designed for a relational model. And it caused a lot of performance challenges and a lot of ongoing maintenance challenges in the system when it came time to make changes. So Google had a real problem. What do we do about this? We have a new type of data. We've got a volume that really is kind of unmatched in the world. What do we do about analyzing it? And what they decided to do was divide and conquer. Rather than scaling up, they said what we would like to do is take a lot of little machines, pull them all together into a true grid, and then use that grid as one big massive compute system. This isn't really a foreign concept to any of us, although we may not understand it, but when you turn on your light switches in your homes, that's coming from a utility grid. So the concept of grid, I know that NASA years ago did a lot with grid computing, and the concept of it wasn't really new, but the challenge of how do we bring it in a way that can handle all this new type of data as well, and also give us the ability to go and analyze that data, that's what Google solved. And they did that with two seminal papers that they published and gave back to the world and made it known to everybody exactly what they were doing. And it was called Google MapReduce and the Google File System. And these were two separate papers that they turned over to everybody else in the world. Those Google papers led us to this craze today that we call Hadoop. The timeline for Hadoop goes back quite a bit further than most people realize. It was in 2003 when Google published those papers for the first time. Then in 2004, you saw the manifestation of those papers in something called HDFS, or the Hadoop file system, the Hadoop distributed file system. And then this MapReduce technology, which basically said, how do I now go and ask questions of my data that is distributed all over these commodity servers? How do I do that? What technology do I use? This is where MapReduce came about. And MapReduce is simply a way of taking a question and distributing that question out among a lot of different machines, and then bringing that data back and aggregating the answer together. That's what MapReduce does. And the first project that was launched was called Nutch, and that started in 2004. But then in 2006, they pulled Hadoop out of that to be its own thing. And then by 2008, it became a top-level Apache project. And when you become a top-level Apache project, that's a pretty good thing, because Apache is the open source foundation that is probably the most widely known and most credible. And when you become a top-level project, it says that you've got clout. You really are here to stay, and it's a very valuable project, and you have a lot of activity and people work on it. So Hadoop came from that evolution from Google, which came from the need to handle a different kind of data and a whole lot of it, but in a much more cost-effective way. While that Hadoop story was happening and evolving, in the meantime, a few years later, after the Hadoop wave started to kick off, another challenge emerged around big data. But now we're on the other side of the equation. Now we're looking at those OLTP systems, those real-time systems. And it turns out they were having some challenges too, although those challenges ended up being a little bit different. So let's go back and see, why were these guys created in the first place? What were they trying to solve? And when we look at OLTP characteristics, the common names that spring to almost everybody's mind are the Oracles and the Microsoft SQL servers, MySQLs, and DB2s of the world. We call these systems transactional systems, which has actually led to some confusion today, because you'll often hear real-time systems today called transactional systems, which is actually proper. That's the exact way it should be called. But sometimes we confuse transactions with complicated transactions, like a banking transaction, where you either have to commit everything or you can roll back all those characteristics. Well, that's a different kind of transaction, but it still was how these systems came to be known for the relational world. And these systems were built around a lot of interactive reads and writes. In other words, very small atomic operations that were happening very, very quickly, whether it was me writing information to the database or me reading information from the database. And you would sometimes hear this also talked about as random reads and writes, which just means that there was an unpredictability of which type of data was going to be accessed at any given time. You just really didn't know. So it had to be designed and optimized around those kinds of things. And it also had to be designed around something called durability. And what durability meant was that if something were to go wrong in the middle of a transaction, I, as a developer, I need to understand whether my transaction made it safely to the database or it did not. Let's say a power outage or a network failure. If I'm handling something like a financial transaction, I better know the state of that transaction when that system went down. And this was a lot of effort and time and energy went into solving this problem for relational technologies to make it safe so that you were never in an unknown state with your data. And then guys like me and many, many others spent lots of time optimizing these things to perform well. Entire jobs and industries and even ecosystems of tools were built to make these things run faster. That's what we were after. Great that they were durable, great that they handled these transactions, but now we have to get faster and faster and faster all the time. Then we hit another challenge with these systems. If you think back to how an application used to look, it was such a nice, simple world. Let's say we were building a web app. We would have a web server, and then we would pick a database on the back end. And it was great. Life was easy. Then the application got successful. More users started to come. More demand was placed on the web servers. And so we solved that by adding more of them. And we said, let's intercept that load and distribute that load across many web servers. And that worked well for a while, but the database still became your bottleneck. And so we said, I wonder if there's a way to start offloading some of the more common requests into a layer that can happen very, very quickly in memory. And we did that through Memcache servers. And we started adding these into the architecture so that the answers could be serviced up very, very fast from an in-memory solution. And that, too, scaled well for quite a while. But you still ultimately had the problem of that single database being your bottleneck. And we took another step and said, well, what if we created some read-only copies? Now, what we did here was we took the data from the main database and we started to replicate it as close to real-time as possible to read-only servers. So these were read-only databases that you could ping when you had a read request. And again, this helped. It really took a lot of load off of that system and freed it up to handle the write activity that didn't have to be interrupted by all the read activity. And this worked great for a while, but you still could not get around the fact that you had a bottleneck when it came to the writes to the database. And this is where things took a little bit of a turn into the twilight zone. For a traditional relational mind who was used to all the principles and properties of a relational system, something happened that kind of blew our minds. And that something was called sharding. And in this solution, we said, it's not enough to have one of these things. We need lots of these things. And we need to now separate the data and partition the data, and we'll pick an index. Maybe if it's by last name, we'll take all last names from A to F, and we'll put them on this batch over here. And then we'll take the G to O's, and we'll put them in another batch, and so on. And we manually partition this stuff into a system that we called a sharded relational system. MySQL was a popular choice, a very popular choice for this type of architecture because MySQL grew up and became popular along with the Web 2.0 movement. In fact, many would say it was absolutely synonymous with the Web 2.0 movement. The problem with this solution was when you look at this, this sort of looks like a database on a bad drug. It no longer can function and have all those characteristics and properties that make a relational database a relational database. And so you start looking and fighting the complexity of this type of system, which ultimately can lead to performance problems. And what you started to see was only the most elite in the world who had armies of the highest level development minds could make this stuff work and scale and perform all at the same time. So you saw this happening in kind of those edge case companies, but it became very complicated and very hard to understand for a traditional relational person. And so what we said was, well, hey, we want to get some of that. We want to do what kind of Google did with that Hadoop stuff. We would love to do that with the relational technology. Why can't we do that? Why can't we scale out easily and make this thing something that's consumable across a bunch of commodity servers all acting together? Great idea, and it was something that we all desperately wanted. But turns out you don't always get what you want. Sometimes you get smacked in the face by reality, and that's what happened here. And I'm going to take you through something that gets thrown around a lot, but unfortunately, I still think a lot of people don't have a good enough understanding of this mystical thing called the CAP theorem. I want to try and demystify that a little bit and just explain about what it is and why it's a problem. The CAP theorem was created by some very smart guys, came out of a project at MIT, where they tried to look at what does everybody want out of this relational technology and how can we deliver that? How can we make it work together? And the first thing that they decided was we want consistency. And consistency is a pretty simple concept. It can be misunderstood greatly because of some of the other ways that it's described in relational technology, but we're not going to get into that level of nuance at the moment. We're just going to talk about consistency as the view into the data and the ability to ensure that the type of data you think is in a field is really in a field. That's consistency. So let me give you a couple examples. If I am running an ATM transaction and I'm here in San Francisco, and let's say my wife is on vacation and she's in Dallas, Texas, and we're both trying to pull money out of our account at the same time, and we're both trying to take $80 out of our account, but our account only has $100. Well, we better be sure that that data is going to be consistently viewed by both of us at the right time so that we don't end up overdrafting our account. And that's the responsibility of the bank to make that happen. Or if I say that I'm going to have inside of a field, this is going to be a numeric field, and it's always going to be a numeric field. Well, then that's going to be guaranteed that that's going to consistently be a numeric field. That's part of what consistency means. And we all love this and needed this in the relational world. The second thing we all wanted was availability. When I put my ATM card in, I want it to be online. When I fire up my web app, I want it to be online. I want to make sure that the system is always there and ready whenever I want to use it. So availability is actually a very simple concept to understand. It means just what it says. Is the system available? So far, so good. We understand these things. But now this is where the new demand started to come into play. And partition tolerance means, if you remember back to that diagram and I showed you we partitioned our data, that's what partition tolerance means. I want to be able to scale horizontally and across many, many different machines with my data distributed or partitioned across that world. So partition you can think of as being synonymous for our purposes here as being synonymous with scale out instead of scale up. Well, what the smart guys at MIT said was you don't get all three. Based on the technology, based on the math, based on the physics of how our systems work, you really cannot have all three of those things at the same time, in the same way, at the same capacity. It's not going to work. So you're going to have to give up some constraints to solve certain problems. And as I said earlier, where the relational technology played really well was between the consistency world and the availability world. I could give you a solid view of your data. It was going to be the kind of data you expected, and I could pretty much guarantee, at least in reasonable terms, that it was going to be available for you with clustering or fast failovers or those kinds of things. But to solve the problem of that scale and making sure the system was available at the same time, this is where the NoSQL movement was kind of born. And unlike Hadoop, that really didn't have the concern over the availability to the degree that a real-time system has, availability was paramount. And it was even pushed beyond the limits of what we used to expect. We used to talk about the 5 nines of availability. You're up for 99.999% of the time. That's not good enough in today's world. When you multiply that math out on how much downtime that is in a year, it starts to be a problem because we have now an incredible demand from our users on our systems that it simply always be available. Think about how frustrated you get when you try to go to one of your favorite websites or when you need to access something on the web. Forget about it even being down. Even if it's slow, you go out of your mind. Everybody gets mad and starts slamming their mouths. So why isn't this thing up and running? And we are now conditioned to have things available all the time. But to make that work on the back end at massive scale requires the ability to distribute that data. Now, what these systems don't do well is handle that consistency the way that a relational mind would think about consistency. And so you have to handle those things in different ways. And some people are working to make that better and better inside their systems, but for the most part, it's handled at the application layer. The developers are now the ones who take the responsibility to make sure that those transactions aren't going to step on each other, and they do that in very clever ways. So when this NoSQL was born, what did it look like? Because the challenge today is everybody wants to throw all these technologies into a bucket with a very large brush and just say, well, it's all big data. It's actually quite nuanced. And if you think about how some of this stuff started, the basic concept was this thing called a key value store that led to an architecture by Amazon called Dynamo that was a fully distributed architecture. But then you had Google come out with yet another paper on Bigtable, which was another way to store the data as a data model inside the database. And in parallel to that, you had these things called document databases, which are not documents like Word documents, common misconception. A document database is really, for those of us that have been around a while, You may remember back in the 90s these things called object databases. That's probably the closest analogy that you would have to a document database. It's a very easy to access model through scripting languages and things like that. And then you had these things called graph databases, which helped you understand complex relationships, network relationships, connections on very complicated paths, what's connected to what and how often. Then these things emerged. And then there was this sort of Cambrian explosion of all these technologies that started to emerge and evolve off of this stuff. And it's happened very, very fast. In my last job at Quest, we used to track this stuff. And a matter of fact, the guy on the bottom of the screen there, if you want to follow a great resource, if you're a relational person and you're trying to understand kind of a bit about this new world, I highly recommend you follow Guy Harrison, good friend of mine, former coworker, and he would bring these lists to me every week and say, we got 5 new ones, we got 5 new ones, and what I've showed you here is not exhaustive. There truly was an explosion of this technology around the NoSQL world. And for me, in my world, in my company, the one that I've chosen after a lot of time being able to look at all these different technologies, I'm here at DataStax, where we do a lot with this one here called Cassandra, which is off to the far right about halfway down the page, which was a blending of really 2 technologies, the distributed architecture of Dynamo and the data model of Google Bigtable. But there are many, many out there in the ecosystem still today. So by way of review, let's think about how we talk about big data, because unfortunately the word is almost useless. It has become such a catch-all phrase, and now everybody wants to be on that bandwagon for marketing. It becomes difficult to talk about. Well, I still really appreciate the way that Gartner defined it, and they really defined it through attributes. And they said that if you have one or more of these challenges, velocity, which is high throughput in your system, variety, logs, blogs, social site comments, in addition to regular data. If you have volume, a lot of it, that's not really hard to understand. We all get that one. Or if you have a complexity in the way that your data has to be handled or captured or analyzed, if you have any or all or some of these 4 problems, and it's not handled well with the relational technology, then you do have a big data problem of some sort. And by way of recap, remember Hadoop was initially built to solve that variety problem, the logs and the blogs and the comments, and then there was a lot of it. And they wanted to do that analysis of that data, but the real key here was beyond the technology, low cost. Because I could now use commodity servers to do this stuff, it started to greatly impact my ability to now keep all of my data as opposed to putting it in that very, very expensive Tier 1 or Tier 2 storage. And then on the flip side of that coin, you had the emergence of different technologies like Cassandra around use cases involving velocity. I've got a lot of throughput coming through my system, very, very fast. I have to keep up with it. I want to distribute that load across many, many servers. I've got architectural demands around making sure my system is always available, but it also has to be massively scalable. That can be complicated if you don't have the right architectures. So this is a little bit of history on how we got where we are. And where are we today? Well, unfortunately, we're living in a world of unicorns, fairies, and big data, where everybody's big data system is all you'll ever need, and we have all your problems, and everybody gets along, and it's just a great, great, great world. And unfortunately, this hype is leading to a lot of misinformation, a lot of confusion. And personally, just coming from my background, living through several changes in technology over the last 20 years, I get very frustrated when this happens. And living at it from the inside, I can only imagine how complicated and hard it is to grasp from the outside. So I'm going to continue to try and give you some stuff that helps you cut through this and helps you understand the reality of the world today. One of the first questions is, who is really using this? Is this for me? Should I care? I mean, I'm not Google. Do I really have that problem, or can I handle this easily with my relational systems? That's a whole webinar all by itself, but I'm going to try and walk you through kind of the evolution as I see it of what's happened in the space. And by the way, these are not DataStax customers in any way. This is publicly available information, a lot of it from the analysis I actually did when I was still at Quest a little over a year ago. But as I said, it started with Google, and then the next stage was still these what I call edge case companies. There just aren't many traditional companies who have the kind of problems that an Amazon or a Facebook or a Foursquare or a Twitter or a Yahoo have. And these folks have armies of brilliant engineers who spend all their time kind of torturing these architectures to make them work in ways that are just amazing when you see it happen. But unfortunately, that's difficult to grasp for the rest of us, kind of a thing. The next stage down was we saw a whole new set of companies emerge that were a blend of kind of newer startup-y kind of companies who were looking at the new technology because sometimes, frankly, it was cool. And we shouldn't eliminate that as one of the factors of adoption of big data. Some of it is definitely psychological. I can tell you when I came out of college back in '92, I had every piece of skill set I needed to write COBOL programs and write JCL and write all the Fortran stuff. I could have done all of that. I was very well prepared to do that. I was not going to do any of that, ever. I was going to say, that is not my future. My future, I want to be in client server. I want to be in the new cool stuff. And some of that absolutely is going on today. But even though it's a psychological reason, you really shouldn't dismiss it, because a lot of times markets get changed by exactly that kind of mentality. Now, that said, they were also still struggling with this scale problem, because these all were companies who said, we can be big. We can see this thing exploding. We don't want to get caught off guard later and not future-proof our system. We have to make sure that we can plan for the future in a way that gives us that room to grow when we're successful. But lastly, you now start to see a lot more household names start talking about this new technology and how they're using it. Come on, John Deere, PBS, these kind of companies you would think, really? They're a big data company? But they are, because people are now seeing the advantages of how they can use big data in new and different ways, even in very traditional companies. So the use cases start to emerge once you start to realize the power of the technology and what the technology can do for you. So if you're wondering really how widespread this is, I can tell you from observation, and a lot of customer names that unfortunately I'm not at liberty to share with you, it is absolutely moving into the mainstream type of companies. Now, it's not coming in at the let's replace everything and start from scratch with this new stuff. It's starting on smaller projects sometimes bigger projects, but it absolutely is making its way into that world. Well, what caused this? Why did it happen? As I mentioned earlier, you had the problem of web applications and mobile devices, and all of this along with increased user expectations, where, again, I simply need to be available all the time, and you better be fast. Don't make me wait. Milliseconds translate into millions of dollars for some companies, even some traditional companies with web properties where they need to do transactions or selling online. So it's still a big problem. And if these were the causes, what were the effects? The effects on the architecture were, I got to be able to scale out. I can't keep scaling this thing up. I have to handle now an incredible amount of velocity that I never had to deal with in the past. I mean, you got to understand, a lot of times when we're talking to customers, it is not at all an uncommon conversation to be talking about how many millions of transactions a second are you going to need on this system. That's common. So hundreds of thousands of transactions, common. That's tough in the relational world. And again, you'll hear people say, that's not true. I can do that. I can make this happen. I can make that happen. You probably can. But the challenge becomes with how far can you really go with that without torturing it to a point where it's simply no longer a relational system. And you have to start thinking about the new technologies and what make these beneficial for kind of the right tool for the right job. Now, this part about rapidly changing apps is worth pausing on for a moment, because when you used to change an app, it was painful. You had to go through change management. You had to go kind of kiss the ring of the DBA and get all those processes done. Well, in this world, you have these things called flexible schemas, which, again, is another webinar in and of itself. But you can just think about it like you are now no longer bound to the definition of your data model. Your data model can change pretty rapidly. Doesn't mean you don't have a data model. You still absolutely should. but you can make changes to it very, very quickly without impacting the rest of the system. And that's a big, big part of why people also will start looking at NoSQL technologies. And then the last bit is what caused this avalanche was open source, kind of. And the reason I say kind of is because if you think about the Jeff Moore crossing the chasm terminology, you've got the innovators and the early adopters, and these guys are willing to go through a lot of pain, and they'll bring in their armies of people. But I tell you, watching an open source technology go through those types of folks, the innovators and the early adopters, is astounding how fast it will travel through that community. When it's proprietary software, often you'll still have to slow down and wait for that. But in this world, it goes very, very quickly. But how do we get across that chasm? Well, this is where you look to companies like a Red Hat or like a MySQL or, in our case, like a DataStax to help you get over that into the mainstream, because it gets tough when you're dealing with open source and you move into that meat of that curve. There are just some things you expect. You want things to work and feel a certain way, and you don't want to fight every single little problem and challenge. And that's why companies like us actually exist. So a couple of points, and we'll wrap up on these. Where do you go next? Where should you go? Well, the first thing I would recommend is think hard about what you want with a given problem or a given application, because this really is about the right tool for the right job. And from our perspective, I can tell you where we see a lot of demand for Cassandra comes around this notion of striving for a continuously available architecture. But at the same time, I'm fighting against three problems that I have to work in conjunction with each other. I want it to be massively scalable so that it performs well at huge scale, but I have to keep it operationally simple, because if I don't, I blow my cost model out of the water. And for something that's continuously available, I also want to access it from anywhere. This is where you'll see Cassandra, which, by the way, in the developer community, you'll often see abbreviated with a C star, which is why I put that in there. This is where I live. This is my world. So I won't speak on behalf of other technologies. I can tell you this is where we play, and this is a very real demand. And in this world, one thing you have to get over is that it's no longer a world of either or. The way that we used to write systems looked like this. You picked a database and you wrote your app against that database. Done. Then if you wanted to move it to a different system, you did that ETL stuff. And you would extract it, transform it, and load it somewhere else. And everything was a one-to-one ratio. It was very simple, and we did this for a very long time. But now the designs are way more flexible. And if you're not comfortable with this kind of architecture, I would recommend that you get comfortable with it very quickly, because it's not abnormal at all. In fact, I'll say this is the absolute norm with all of our customers. When I go in and when I look at what they're architecting and how they're architecting it, through a services layer that sits between the app and the data stores, you'll have an Oracle database doing its thing, but Oracle's put in its proper place. And then you'll have a NoSQL database that maybe isn't meant to scale. Maybe it's going to handle some metadata or some login information. Then you might have a NoSQL database like a Cassandra that's going to scale incredibly broad. And then you might need Hadoop as well. And so get used to the fact that it's now a world of a heterogeneous back-end data store. This is how modern apps are being designed. The next thing would be to think ahead, think through the use cases. The challenge was when we looked at that world of how we used to handle real-time and data warehousing, this had problems. It really did decouple the development process, and the business suffered for it because the business would then lag behind because we had to wait too long for stuff to happen from the OLAP world, from the data warehouse world, and we would break that virtuous cycle of how we would build an application. And one of the things we're trying to do as a company, and quite frankly, me in particular, and one of the reasons why I came here is I lived through this problem, and it was painful having these different systems. And so one thing we're trying to do as a company is help you in advance with any use cases that the business is going to throw your way. So we take Cassandra as our foundation with its fully distributed architecture and ability to do great massive scale and keep performance and operational simplicity, and we bring some of these other technologies into that same platform, and we call it DataStax Enterprise. So if you need to look at Hadoop for batch analytics, or if you need to do real-time search with something like Solar, we want to have that ready for you so that you don't have to fight with your infrastructure and you can focus instead on the application. And that's one thing we're trying to bring to the community and to the table as a commercial company. The next thing is really think through your architecture choice. This is the #1 regret that I hear from customers who come to us who've maybe tried a different technology and didn't think through the architecture. So this can bite you if you prototype too quickly, and then suddenly you realize when you go to scale, I've got a problem. And so what you need to think about in this world, when you think about your architectures, you really have two choices. You have what's called master-slave, and you have fully distributed. Now there's nuances beyond this, but in general, these are the two. And you can think about a master-slave architecture like a traffic cop managing traffic. Somebody has real teeth, real authority to stop the flow of traffic, to make sure that a certain car goes in at a certain time and in a certain way. Whereas a fully distributed architecture looks more like a roundabout, which is a tough concept for a lot of us in America. We struggle with these when we encounter them, but they're very common in the rest of the world. And in this system, it's a self-governing kind of come on when you need to come on and exit when you need to exit. And you don't have that traffic cop that has the authority to simply stop traffic. It's designed to let traffic flow in and out at all access points. And that has consequences. So if you think about setting up, what does a master-slave architecture tend to look like? Well, you can have a situation where, hold on, I'm having a little challenge with the slides here. So you can have a situation where if you want to have a master-slave architecture where you've got 4 data nodes and you've got to set up a master to handle that, then you need to have some other things in there to help control that and talk to that. So you'll have these coordinator nodes, but then you got to have lock manager nodes, and then those all have to work and talk to each other. And then ultimately all this has to work in conjunction before you can ever get to the point where you have all of your data nodes talking to each other. So this is going to have real implications on how you think about scaling and designing your system. And it's going to run into problems down the road if you haven't thought through, well, what if I want to do a different type of architecture? What if I want to do something across data centers or in the cloud? You just have to think and understand about how these things work. The fully distributed architecture is a little different. In this architecture, we have a situation where you've got a fully distributed environment where every node works the same. Hold on a second, it looks like we're off on our slides a little bit. You have a situation where every node works the same, every node is of the same type, and these nodes all communicate directly with each other in a way that you don't have this concept of a master, just like the roundabout, where you have a situation where every node type is the same. Well, what are the implications of this? The implications are that now, with a system like that, you can start spreading and distributing your workload across multiple data centers. This is now becoming a very common type of architecture where you have a physical data center that is replicating to another physical data center, and then you're in the cloud, and these are all working together. But it's not just replicating from one central point. You are literally having everybody access all the system all at once from anywhere. So they can hit it from the cloud, they can hit it from a regional data center. Why would you want to do that? Well, one reason might be disaster avoidance. You simply don't even want to deal with a situation where the data center is no longer available because of a storm or an outage or something like that. Another reason is performance. You want to push the data closer to where your users are, but you want it to be the same database. And in this model here, you're looking at a single database that spans multiple things. And in this case, we have like a DataStax enterprise scenario where some of the workload might be Cassandra. Some of the workload could be Hadoop, some could be search, and you can spread that workload in different data centers, becoming very, very common in modern real-time applications. And the last piece that I'll leave you with is just to educate yourself. Learn as much as you can. And we're trying to help you with this kind of thing. So you can come and find a lot of great resources at our websites that are case studies and interviews with real customers. Customers, as you guys probably know, are very difficult sometimes to make referenceable because they don't want to tell the world what they're doing and what they're working on. That said, we work hard to try and give you as many real-world use cases and interviews as we can. So if you go to our site, you'll see I think we have 20 or 25 of them up there right now, because I don't think there's any better way to learn than there is to just look at what other people are doing and understand what they're doing and hear it from them rather than hearing it from us in our marketing. Next thing is we just had a great conference. We had about 830 people, I think, show up, and all those presentations and videos are online. Here again, you get to hear it right from the people who are living and breathing it. We got white papers that cover everything from relational, people trying to grasp this stuff, to where do I even begin, why do I care. We've got existing webinars that are up there. We've got trainings that we do around the country. But one thing I would really encourage you to do is, if you're interested in this and you want to kind of get up to speed, we're introducing a new webinar series that is a very systematic approach to educating you through the process. And over the next couple of months, you can actually work your way up from what the heck is NoSQL and why do I care, to by the end of the time you'll be actually doing a sample app, or you can have some folks in your company doing sample apps and learning and understanding about how to do even some deeper integration with some other technologies. This is the kind of stuff we want to make sure that we're educating you to keep you up to speed. All this stuff is free. You can come on and sign up for all of these, absolutely no strings attached. We just want to help educate the community on what and why is going on. So with that, I'm going to wrap up the main presentation part and bounce over here and see if we have any questions that I can take.
Thank you, Billy. That was an excellent presentation. Before we begin with today's Q&A, please fill out the feedback form that has opened on your computer. To complete the form, please press the Submit Answer button at the bottom of the page. Thank you in advance for filling out the feedback form. Your participation in this survey allows us to better serve you. And now, on to the question and answer portion of the event. As a reminder, to participate in the Q&A, just type your question into the text box located below the media player, then click the Submit Question button. We have some questions, and I'll read the first one. Can you explain a bit about tunable consistency and eventual consistency? Billy?
Sure. I'll keep this quick because it can be complicated. Again, there are different types of consistency when you're talking about a database technology. One of the biggest problems is what we call data consistency. Is if I update a field and somebody else comes into the system, but perhaps they're on a different side of the planet. They're over in London or something. And they want to look at that same data information. So I update that the number of people on a flight is 130, but the previous number was 50. Well, now that person in London wants to look at that, and what are they going to see? Are they going to see 130 or are they going to see 50? Well, by default, one of the ways we handle that is called eventual consistency, which means eventually, when the system gets around to it, that guy in London will see 130. But there are cases where that's not acceptable. You may need to make sure that everybody is truly looking at the same data at the same time. And for that, we have something in Cassandra called tunable consistency. And for that, a developer can issue a query, and for that query, they can say, when I update this field, when I update this flight information from 50 to 130, I want to make sure that everybody is going to see the 130. And that's going to take longer, which is going to affect my availability, because we're back to that cap theorem thing. You know, you're going to give something up when you do that, but we let you do that per transaction. So you get to choose, and when you get to choose, that's what we call tunable. You get to decide what level of consistency you want. Do you want the whole data center to see the same data? Do you want multiple data centers to see the same data? Or do you want to not even worry about it at all? Maybe it's of a type of data that just simply doesn't matter. Which, by the way, is more common than you think. Unfortunately, many of us who come from the relational world, our minds always go to the need for absolute consistency. But when you really think about it, in many, many, many parts of your application, you don't need that. And so, but we try and give you the choice. Now, there are different types of consistency that, frankly, NoSQL solutions, near as I can tell, are never going to solve, like referential integrity, things like that. So, because that just doesn't exist in a relational model. But that's what we mean when we say tunable consistency. You can tune the data consistency, and you can do that per transaction.
Excellent. Next question. If we move our data center to Amazon and run Cassandra, should we consider using SSDs?
Yeah, well, I think that's even a question for local data centers as well as Amazon, certainly, and we have customers doing both. We have very large implementations on Amazon. Netflix is one of our public ones that talks a lot about what they do, and they are in fact an SSD user. But then we have people who ask that exact same question in data centers. Here's the thing. Again, one of the things about Cassandra that I love, just the kind of the geek in me, is that you do get a lot of flexibility. And one of the things that they added in the last release of Cassandra is the ability to segment workloads to certain disk types. So suppose you have a certain table for people with relational minds, think about it like that. You have a table that is very performance intensive and demanding. Well, perhaps you want to route the workload for that table to an SSD bank. But for another part of your application where it's not as important, you'd like that to route to lower cost magnetic disks or spinning disks. You can absolutely separate that workload, and you can change that over time. So you have a lot of flexibility, and really it depends on your budget. Cassandra is absolutely optimized for SSD performance, and some of the things that it does is pretty phenomenal, actually. That we have some great resources on this. If anybody wants to email me directly or send a note to us at DataStax, we'll get you a great white paper on that. But yeah, SSDs, I think, are a big, big, big part of our future. And I think for a long time to come, it's going to be a mixed workload environment of some workloads going to be on the very, very, very cheap spinning disks, and other workloads are going to be on the more affordable nowadays SSDs.
Thank you. Now I'll move on to the next question. We are looking at Hadoop for a system to do advanced analysis of ticketing data. Should we be considering DataStax, and why?
Yeah, I would say absolutely, because the thing about the Hadoop systems are when you have a Hadoop type problem, you're typically looking at some sort of deep analysis. You're wanting to analyze something. Well, what are you wanting to analyze? Typically, the data that you're wanting to analyze comes from some real-time system. I mean, this isn't quantum mechanics. Things just don't pop into existence, right? So the data comes from somewhere. When you start thinking about that real-time system that you're building with Cassandra, this is, again, where DataStax comes in and says, let us bring the other technologies to that data. So we can come in and absolutely configure that Hadoop workload right on top of that same data. And what we do when we do that is separate the workloads. And anybody that's lived through the past on, well, wait a minute, why do we have data warehouses? Well, because the workloads killed each other. The cool thing about Cassandra's architecture is that because it is fully distributed, because it is not master-slave, we can partition out different workloads in DataStax Enterprise on a Cassandra ring and say, we want these 10 nodes or 20 nodes to be operating as Hadoop nodes. We want these 30 nodes as Cassandra nodes. We want these 5 nodes as search nodes, whatever. And you can add to that capacity in each one without stepping on top of each other. So sure, absolutely, you could look at us for that kind of use case. I would say probably once you start doing that, you will probably start looking at it a little more holistically. And instead of looking at just Hadoop for this, and then I'm going to go look at Cassandra for that, this is where you probably take a step back and say, do I want to fight all that? Do I want to fight the integration of all those systems? Or would I like to have all that nicely packaged together and integrated, certified, tested? That's DataStax Enterprise. So it really depends on where you are on that curve. Think about that chasm, crossing the chasm curve. If you're to the left, you might well want to do that, fight with all the, because it's fun, you enjoy it, and you learn a lot. But when you're ready to solve business problems and not get so hung up on the infrastructure, whether it's Hadoop or whether it's Solar or whether it's Cassandra, sure, we would love to help you at DataStax.
Excellent. Next question. Are there any user-friendly GUIs for Cassandra, like Toad for Oracle?
Yeah, so there are a couple of things. First of all, what we provide with DataStax Enterprise is a tool called Op Center. And with Op Center, you have a web-based application that's completely graphical that lets you, from there, you can go in and do all your management and your monitoring, all the stuff you would expect to do when you're running a system. Because it is web-based, it's great, it's easily accessible anywhere, but it also handles the mixed types. So you got not just your Cassandra environment, but your Solar environment, your Hadoop environment, all in a single pane of glass. So that's one thing. Second thing, a little plug for my former company, just because it was one of my products that I launched when I was there. It's called Toad for Cloud Databases. I think it's still actually free, the download for Toad for Cloud Databases. So you can go to their site. And what's cool about that is if you're a relational person, it's beautiful for you because now you can connect to your relational data sources and some of your NoSQL data sources, not just Cassandra, by the way, even the other ones. So you can do all that from a single product. And Quest going through the process of being acquired by Dell right now, but they're going to be very true to their software pioneering in the database space. And I'll give a little plug to my friends there. You should go check them out as well.
Thank you, Billy. Looks like we're out of questions. Any closing comments?
Just that, if there's one thing I want to leave you with is please don't be afraid to ask questions. I see this all the time. I go to a room and I'm doing a presentation. There might be a couple hundred people in the room, and I can just tell that there are really good questions there that people are afraid to ask because they feel like everybody else around them that they've got it. And they feel like, well, I don't want to ask that question that seems so simple and so obvious. Like, why did these things get created in the first place? Why can't I do that with relational? What do you mean by fully distributed? I don't understand that. Like, isn't all this stuff distributed now? Just ask. If you don't want to do it in a public setting, come to us, call us, email us, go to our website. We'll try and help you out. We've got great community resources to help you out. We want to be the company that helps you get through this curve. You got, again, 20 years I've been around relational databases. It's in my blood. I understand how hard it is. We start talking about data models, oh my goodness. That's where you're going to go through a trippy mind experience. You really got to reset how you think about these things. But put in a little bit of time doing that. When you do, the benefits that are going to come out of it on the other side are going to be fantastic. You as a relational person, for those on the call, you are incredibly valuable for the next 5 to 10 years because developers love building stuff, not so great at maintaining it over time. And DBAs can bring so much institutional knowledge from the company. And in this world of both and, where you're going to have all these technologies, wouldn't it be great if you could sit down at the table as a voice of reason to say, hey, you know what? We need to use relational for this piece. I want to use Cassandra for this piece. I want to use this for this piece. You can become a trusted advisor and a true administrator of the data, not just a database. Because you know what? We're just a database. Don't let that freak you out. We are still a database, and people with relational knowledge have a lot of great knowledge. So don't be afraid to ask the questions. Educate yourself. Ask them in a safe place if you need to. We'd love to help with that. But you are in a position to be incredibly valuable over the next 5 to 10 years. So don't be afraid of this movement. Embrace it. Embrace it and really use it as a way to catapult your career.
Thank you, Billy. Excellent closing comments. For more information related to today's webcast, please visit any of the resource links open before you. Within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. Additionally, you can view today's event on demand by visiting www.netseminar.com. Thank you for attending today's webcast, Bridging the Great Divide, the Relationship of RDBMS and NoSQL, brought to you by Information Week and DataStax. This webcast is copyright 2012 by United Business Media, LLC. The presentation materials are owned by or copyrighted, if that is the case, by Information Week and DataStax, who are solely responsible for its content, and the individual speakers are solely responsible for their content and their opinions. On behalf of our guest, Billy Bosworth, I'm Eric Bruno. Thank you for your time and have a great day.